Hello and welcome back. Before I continue the lecture, let me start with the riddle, which is important for future math teachers. Okay, here's the riddle. Someone asks you to compute the derivative of arctangent t plus arctangent 1 over t outside 0. When you do the computations, you will find that f prime is 0. So you conclude that f is constant. However, you notice that f of 1 is arctangent 1 plus arctangent 1, so it's pi over 2, and f of minus 1 is minus pi over 2. So we get two different constants. What's the problem? What's wrong? I want you to think of it a little bit. Okay, now let us go back to section 2.2, and the main result of this video is to prove that a holomorphic function on an open set is analytic. So the key ingredient is actually a particular version of Cauchy's integral formula, or Cauchy's integral formula in a special case. We shall prove later in the next section a more general formula, but this formula is enough for us. So consider a holomorphic function on an open disk of center Z0 and radius r. And now inside this disk, consider a circle of the same center, but with radius smaller, with radius r0 smaller. So we have a circle inside the disk with the same center. Then, for any z inside the smaller circle, we can represent f by an integral. Okay, and this is the key to proving the next theorem. Okay. Now, this result is actually a consequence of Cauchy version 2. Okay, applied to some special function. So, for any z inside the smaller disk, consider the function g of u defined on the bigger disk and given by f of u minus f of z over u minus z outside z. So if u is different from z. But if we want g to be continuous, you must set g of z equal f prime of z, because the limit of this ratio is f prime of z. Now, so what do we have now? So g is actually, by construction, is continuous on the disk, bz0r, the same as for f, and apparently is holomorphic only at the disk without z, the punctured disk, if you like. Actually, we shall see later that f is holomorphic on the whole disk, but we don't know that. You don't know that yet. Okay, so we must go step by step. So G satisfies the conditions of Cauchy version 2, and therefore the integral over the boundary of any triangular region in the disk must be 0. Now, since the disk is convex, we already observed that this is equivalent to saying that the integral over any triangular loop, this should be loop here, so the integral over any triangular loop of G is 0. And if you recall theorem 2.24, then G has an antiderivative, and therefore the integral over any loop is 0, not just any triangular loop. Okay, so G has an antiderivative inside this convex set, right? Actually, we already observed that earlier. Okay, so locally, G has an antiderivative, if you like. And therefore, since G of u equal this ratio, because now if u is in gamma and z is not in gamma star, so therefore G must be equal to this Newton's ratio. So I get that the integral of this ratio is 0. Here we integrate with respect to u, fixing z. Okay, but z is arbitrary. Okay, so let us explicit this. Let us split it into two parts. Okay, so these two integrals are equal. Now, in the second integral, z is constant, so I can put the f outside. And there is a 1 over 2 pi I actually here missing. And this has a name actually. 1 over 2 pi I times this integral, as you saw in the previous video, is just the index of gamma with respect to z, right? There's the 1 over 2 pi I here. Now, how to compute that index? Well, this is easy because we know that z is inside the disk, okay, the disk gamma. So, but we said that the index is constant on the components. So the index of gamma with respect to z is exactly equal to the index of gamma with respect to z0. And you already computed that, and you found by going back to the definition that is 1. Okay? And that's it. You are done. This concludes the proof. So f of z is this integral. Okay? So this is very easy. Now, I will leave you with 2 exercises that I usually do in class. So I let the students do it in class. But now, unfortunately, this is very difficult now. So try to pause the video and solve so compute these 2 integrals. Okay, and you can write also here 1 over u square if you like plus 1 du in order not to confuse. Okay, but anyway, so try to solve these 2 questions before we continue as a direct application of Cauchy's integral formula in a particular case. Okay, so now we are ready to prove the main result of this section, the first main result, because there are so many beautiful results to come. Analycity of holomorphic functions. So I announced this result in chapter 1 before, but now, we didn't have the tools to prove it. Now we have. So we have a holomorphic function on an open set omega, and we want to prove that it's analytic on omega. So pick a point, an arbitrary point z0 in omega. Since omega is open, there exists an open disk of center z0 and radius r contained in omega. Okay. Now take r0 less than r. Okay, so we have now a circle inside the disk as before, right? So we work now on this, not on the whole of omega, but just locally about z0. Okay, so we can apply Cauchy's integral formula and represent f in this integral, as in Now, what we are going to do is elementary. Actually, we did something similar in chapter 1. So we will expand 1 over u minus z, or f of u, as a power series and integrate term by term. Okay, how to do that? So when you add and subtract z0, we factor by u minus z0, we get 1 over 1 minus this number, complex number. Why? Because now we can expand this in a geometric series, 1 over 1 minus q, as you know. And why we can do that? Because by assumption, the modulus of this guy is less than 1. Why? Because u is where? U should be in gamma star, so on the circle. So the distance to the center is r0. Okay? So this is just modulus of z minus z0 over r0. But z actually, well, it's in bz0 r0. So z minus z0 is less than r0 strictly. So the ratio is less than 1. Therefore, we can expand in a geometric series, but we have to put n plus 1 here because we have this constant. And we just multiply by f now. We have this representation of f of u over u minus. Now, we want to integrate term by term, but to do that, we just have to justify. Actually, this is true, actually. Yeah. So the integral of this guy is the integral of the sum. Now, to justify the interchange of the integral and summation, we just have to prove that the convergence is uniform. Okay, and indeed, convergence is uniform on gamma star. Why? Because gamma star is compact and f, or modulus of f, is continuous. So modulus of f is bounded. So choose a bound, capital M. Then, if you take the modulus of the general term here, then the modulus of f of u is less than m. The modulus of the denominator is just, this distance is just r0 because u is in gamma star. Okay, so the variable of integration is on the circle of centers at 0. So I get r0 to the power n plus 1. And this is just the modulus. So I put the m over r0. So I rewrite in this way if you like. And now this is the general term of the convergent series, because you observe that this is less than 1. Okay, so the general term of this series is bounded from above in modulus by the general term of a convergent series of positive terms. So this is what we call what do we call that? Normal convergence. Okay, we call that normal convergence. You can call it the Weierstrass M test if you like. So normal convergence, as you may know, implies uniform convergence and absolute convergence. Okay. Therefore, we can interchange term by term. We can integrate term by term. So we can interchange sum and integral. And when you do that, so we put the sign, the summation outside. And you call all, so this constant times this integral, you just a constant, doesn't depend on z actually. Okay, it depends on z0 and n. So you call them an. So we have a constant an that depends on z0 and n multiplied by z minus z0 to the n. Okay, which I put it outside the integral. Therefore, and this is true for every z in this disk. So we can write f of z as a power series about z0, where the coefficients are given by this formula. Okay, so not terribly difficult, but we had to prepare for that. Okay, so not trivial. Now keep in mind this formula because we shall return to it later. So the coefficients are actually given by a formula. There's a formula for the coefficients. Okay, now remark, if f is analytic at the point z0, then it's analytic on a neighborhood of z0. And this was not true for holomorphic functions, because we can have a function which is holomorphic only at a point, but not holomorphic on a neighborhood. So this is one of the differences. Okay, so why this is true? Because if f is a holomorphic, so if f is analytic at z0, then it's holomorphic on a neighborhood of z0, right? By definition, because it's the sum of a convergent power series. Okay, and according to the previous result, then f is analytic. So actually, f is analytic on u. Why? Because if you pick any element z1 in u, then you can find a disk of center z1 contained in u, right? But the function f is, since it's holomorphic on u, it's analytic at z1. Okay, so it's analytic at every point of u, since z1 was arbitrary. Okay, so analytic at a point implies necessarily analytic on a neighborhood of that point, and this fact actually can be proved without the previous theorem, actually, by using the theory of power series, but we didn't do that. So it's just a consequence of our main theorem in this chapter, this section. Now, the second important remark is, what can we say about the radius of convergence of a holomorphic function on an open set? So we know that if you go back, we succeeded in writing our holomorphic function as a power series about z0, okay, for every z in, okay, so in a neighborhood. Okay, but what can we say actually about the r0 here, or the r? Can we estimate the radius of convergence without doing all these computations? Yes. So we just have to go back to the proof. Okay, so suppose that f can be extended to a holomorphic, so cannot be extended to a holomorphic function outside omega. So in other words, omega is the biggest open set on which f is holomorphic. So see, the complex plane is now divided into two parts. Omega, which is now the set of points where f is holomorphic, I call them regular points, and points outside omega, or in the complement of omega, whose point I call singular points. Okay, so every complex number is either a regular point or a singular point. Okay, and omega is open, so the complement is closed. Okay, so if you go back, so we know that f can be expanded in the power series. And now I claim that the radius of convergence of this power series is the distance between the point about which we are expanding to the complement of omega, to the set of singular points, if you like. Okay? Now, it's possible that r equal plus infinity, because it's possible that f is holomorphic everywhere, so omega equals c, and therefore this is empty. And it's a convention, actually, that the distance from a point to the empty set is usually set to plus infinity, if you like. Okay, because the infimum of the empty set can be set by convention to be plus infinity. So we include this case, but this case is trivial, actually. Okay, this is the case with the exponential, for example, or cosine. The radius of convergence is plus infinity. Okay, so in words, the radius of convergence is the distance from Z0 to the set of singular points. Why this is so? Let us go back to the proof of the theorem. At the beginning of the proof, we took, so Z0 is an omega, and omega is open, so we found an open disk inside omega and of center Z0. Now, take the biggest such open disk. Okay, so here's the picture. This is Z0 and this is omega. Take the biggest possible disk contained of center Z0 and contained in omega. Okay, and you can do that by taking r to be the distance from Z0 to the complement of omega, okay, as in the picture. So this is I call small r. Okay, now I will prove that small r equal capital R if r is the radius of convergence. Okay, so this is the picture. Of course, I can take in the proof, any number smaller will do, but in order to determine the radius, I'm going to take the biggest such radius. Okay. Now consider an arbitrary point r0 less than r, this maximal radius, if you like. Okay, so the proof. If you go back to the proof, we know that the series is convergent inside this smaller disk. Okay, so we can, then necessarily the radius of convergence is at least r0, right? By the property of convergent power series. Okay, so capital R is bigger or equal than r0, but r0 was an arbitrary point less than r. So if you like, I can let r0 tend to r, and then I get capital R is bigger or equal than small r. So this is half of the proof. Okay. Now I want to prove the reverse inequality. Okay. We reason by contradiction. If r was strictly less than small r, if capital R was strictly less than small r, then I go back to the definition of R, which is actually the infimum, the distance from Z0 to omega C. So it's an infimum. So anything bigger, so R is the largest lower bound. So anything larger is not a lower bound. Okay. So we used that several times, actually. So what does it mean? It means that there exists a point inside this disk, a point in omega c, right? If you go back to the definition. And this is a contradiction because F is holomorphic on the disk of convergence, right? So it cannot contain a singular point, right? Yeah. So therefore we have equality. So we can conclude that the radius of convergence is the distance from Z0 to the set of singular points. Okay, let us illustrate this on an example. Okay, consider the function given by Ez over 1 minus Z. Actually, this was Z squared. There's an error here. Yeah, we can consider actually Ez over 1 minus Z. It's not terrible, but Z different from 1. So there's what actually, yeah, I was thinking of another problem. But so consider Ez over 1 minus Z for Z different from 1. Okay, so please, it's an error. Now, so what is omega here? Omega is C without 1, because 1 is a point of singularity of F. 1 is a singularity because F is not holomorphic at 1. Okay, so we know that without computing anything, we know that the radius of convergence about 0, let us say, okay, is what? Is the distance from 0 to omega to the complement of omega, which means to 1. The distance from 0 to 1 is 1. So I know that R equal 1 without computing anything. Okay. Now you can do the same thing if you like with Ez over 1 plus Z squared, where Z is different from I and minus I. Same thing. I can ask you such question in the exam. Okay. Now, in this case, we can compute with some difficulty. We can compute explicitly the coefficients an. So I will leave you with a challenging exercise, actually. So first question is to compute explicitly the coefficient, just in this case, as that different from 1. And second question, show that in the context of the previous remark, the distance from Z0 to the singular set is also equal to the distance from Z0 to the boundary. And this was clear in the picture, actually. But prove this rigorously. And last question, show that there exists a singular point on the circle of convergence. Okay, so this is just the circle of center Z0 and radius R. So we have to show that the circle of convergence meets the set of singular points. So therefore, we can say that the radius of convergence is the distance from Z0 to the nearest singularity. This result is more precise than the previous result. Okay, because the previous result just say distance from Z0 to omega C. But here I'm saying that the distance is achieved. So, but this is not trivial actually, because omega C is not compact, not necessarily compact. And the boundary need not be compact as well. Okay, so the distance from a point to a closed set need not be achieved, but in this case it is achieved. So the infimum is actually a minimum. Okay, so this concludes this video, and see you soon. Thank you for your attention.